Checking independence. A homeowner has smoke alarms installed in the dining room adjacent to the kitchen and an upstairs bedroom above the kitchen. The two-way table shows the probabilities of smoke in the kitchen triggering the alarm in the dining room D or not, and in the bedroom B or not. We have the summarized table or the modified version of the information given in a table. The total probabilities add up equals to 1. The probability that the smoke in the kitchen triggering the alarm in the dining room is 0.95. The probability that the alarm will go up in the bedroom is 0.4. But this is the given information. There are two events, D, dining room, and B, the bedroom. Specifically, smoke in the kitchen triggering the alarm in the dining room is the event D. Smoke in the kitchen triggering the alarm in the bedroom is the event B. To determine if events B and D are independent, what two probabilities should we compute? There are two events B and D. The two events are independent if the probability of D is the same as the probability of D given B. So if we can compute the two probabilities and compare, then we can determine whether B and D are independent. Alternatively, we could compute the probability of B and the probability of B given D. If we can compute the two probabilities and compare, then we can see whether B and D are independent. Either one of those two pairs, not both. We do not need to do both, just one only. And so for part B, find the probability that the event D given B and the probability of D. From the table, we see that the probability of D is 0.95. This is the D row divided by the grand total 1, which is 0.95, which is what we were given the probability that the smoke in the kitchen triggering the alarm in the dining room is 0.95. Now, the probability that the smoke in the kitchen triggering the alarm in the dining room given the smoke in the kitchen triggering the alarm in the bedroom, or the probability of D given B, is, by definition, the probability of D and B divided by the probability of B. And this is how we compute the conditional probabilities. From the table, we see that in the denominator, the probability of B is 0.4. This is the B column. And D and B is the intersection of the row D and the column B, and that is 0.38. This is 0.95. Comparing the two probabilities, we see that they are the same. Since these two probabilities are the same, we can say that in part C, the events B and D are independent. And again, that is because the probability of D equals the probability of D given B.